Big O notation, the language of growth. This is the most important notation in introductory computer science, and despite the scary name, the core idea is short. By the end of this video, you'll know what Big O actually measures, the two rules that simplify any expression into clean Big O, and your first complexity class, data structures and algorithms foundations. Big O notation. A quick look back. Previously, we said we study algorithms a priori, by reasoning about the code, not by running it. We saw the four-step frequency counting technique. Number each statement, count how many times each one runs, add them up, simplify. Today we meet Big O. Big O is the mathematical language that a priori analysis uses to express its answers. It's a 100-year-old notation from mathematics that turned out to be perfect for talking about how code scales. Frequency counting gave us a polynomial, like 2n plus 3 or 3n squared plus 5n plus 7. Big O is how we read it. It tells us at a glance how that polynomial behaves at scale without bothering with the parts that don't matter. Big O measures growth. Important, Big O does not measure seconds. It does not measure memory usage. It does not measure energy consumption. None of those. Big O measures the shape of how work scales with n, where n is the size of your input. Maybe n is the length of a list. Maybe n is the number of users. Maybe n is the size of a file. Whatever n is, Big O describes the relationship between n and the amount of work. The clearest test: if you double n, what happens to the work? Stay the same. That's constant time. Double, that's linear. Quadruple, quadratic. Or does the work explode beyond what's reasonable? That's exponential. That answer is Big O. The core idea is figuring out which of those shapes your code has. Two simplification rules. With these two, you can turn any polynomial from frequency counting into a clean Big O expression. They're the smallest set of rules you need. Memorize them and you'll use them for the rest of your career. Rule 1. Drop the constants. O of 2n equals O of n. The 2 in front doesn't change the shape of the curve, it just scales it. Doubling each step adds a factor of 2, but the work still grows linearly with n. Same shape, so we drop the constant. Rule 2, drop the lower terms. O of n squared plus n equals just O of n squared. At large n, the n squared term completely dwarfs the n term. At n equal 1 million, n squared is 1 trillion and n is 1 million, a difference of 6 orders of magnitude. The lower terms become irrelevant. What's left after applying both rules is the term that matters when n gets large. The dominant growth shape, that's the Big O. Let's walk through a worked example. Take the polynomial we got from frequency counting. Imagine after counting a function's statements, we got 3n squared plus 5n plus 7. Looks complicated, it's not. Apply rule 1, drop the constants. The 3 in front of n squared, the 5 in front of n, the 7 by itself, they all go. We're left with n squared plus n plus 1. Apply rule 2, drop the lower terms. The n is smaller than n squared. The 1 is smaller than both. So they go too. We're left with just n squared. Clean the answer, O of n squared. That's the Big O class. The function's running time grows as n squared. Why is this fair? Why are we allowed to drop all those terms? Look at the numbers. At n equal 1 million, n squared is 1 trillion operations. The 5n is 5 million operations. That's a rounding error compared to a trillion. The constant 7, completely invisible. At large n, only the n squared term matters. The simplification rules respect that truth. Now let's meet our first Big O class, O of 1. Constant time, same work, no matter the input size. The simplest possible complexity, and one of the most useful. Take a concrete example. What is the first item in a list? In code, that's list bracket 0 bracket. Go to position 0, read the value, done. Now ask, how many operations does this take? The defining feature, whether your list has 10 items or 10 million, the work is the same number of operations. The runtime doesn't depend on n at all. The function ignores the size of its input. Whatever your list has, 10 items or 10 million, the work is the same. If the work doesn't grow with n, it's O of 1. That's the rule. One operation done, and the same operation no matter the input size. the class you reach for when you want lookups that don't slow down as your data grows. What does O of 1 look like in actual code? Let's walk through 3 examples. Tayin is in there, Nindande, seed samples, and pay attention to why each one is constant. First, R at position 5. Array indexing behind the scenes, the runtime knows where the array starts in memory. To get the 5th element, it adds 5 times the element size to the start address. Direct jump, 1 step, no loop, no search. Second, D at the string key, dictionary lookup. The runtime hashes the key into a bucket number, then jumps to that bucket and returns the value. The size of the dictionary doesn't matter. The hash always takes the same amount of time. 1 step. Third, stack.push, stack.pop. These modify the top of the stack, adding or removing 1 element. The runtime knows exactly where the top is. No scanning, 1 step regardless of stack depth. The pattern across all 3, whenever you can get to your answer without a loop, it's probably O of 1. Direct access, no iteration. That's the smell of constant time. There's a subtle catch with O of 1 that confuses a lot of beginners. Let's look at it. Take Python's list.append. Add an element to the end of a list. Sounds like a constant time operation, right? Most of the time, yes, is 1 step. But every so often, the list runs out of allocated room. When that happens, Python allocates a new, bigger list internally, typically twice the size, and copies every existing element over to the new list. That copy is n steps, not 1. So if we look honestly, most calls cost 1 step. The occasional resize call costs in steps. The question is, on average, what's the cost per call? Turns out, because the resize happens less and less often as the list grows, the average works out to about 1 step per call. The expensive resize is rare enough to amortize across many cheap calls. This is called O of 1 amortized. The formal term, it means average over a sequence of many calls, the cost per call stays constant. Any single call might be slow, but the long-run average is constant. This is the kind of guarantee dynamic arrays, hash tables, and many other data structures give you. Here's where we are in the series. Previously, in the priority analysis, reasoning about code without running it. Frequency counting gives us a polynomial in n. This video, big O, is the language we use to read that polynomial. 2 simplification rules, drop constants, drop lower terms, and our first class, O of 1. Constant time with the amortization caveat. Coming up, the 6 big O classes you'll meet in real code, each one walked through with examples. Log n, linear, n log n, quadratic exponential, the whole hierarchy. The best way to predict the future is to invent it. Alan Kay said this in 1971, talking about computer science research. It applies to big O too. Big O lets you predict how code will behave at scale before you ever release it, before any user touches it. You're inventing the future of your function's performance with math. And that's the closest thing software engineering has to seeing the future. Every senior engineer eventually internalizes this skill, and you're well on your way. Thanks for watching. If this video helped you finally make sense of big O notation, please like, subscribe,